times the names are actually to give credit to the people that discovered them. Yeah. But understand too, they started naming these elements long before they started putting them in order and making up the periodic table. So one preceded the other. All right, guys, let's get started. I know that we talked a couple days ago about the way the rest of this unit was going to unfold. So let's be sure. So guys, today we are going to get done with oxidation reduction reactions. There's no possible way we can turn this into 2 days. So we'll do redox today. We will do solution, we'll do molarity and titrations on Thursday, which means Monday coming back after the weekend will be your first unit test. So guys, with that said, we did this. We said, let's talk about weak and strong acids and bases and have that conversation, and then go back and revisit any of these questions that you needed to. So I think the entire assignment is in play, if I remember correctly. So guys, what do we need to talk about acids and bases at the tail end of chapter 4? We okay? $33? I think so. It's always a great thing when the first 5 words are, it is interesting to note. Sorry. What is the question? Okay. It says, is there any correlation between the anions that form when each of the strong acids dissociate and the anions that normally form soluble ionic compounds? So, Sophia, I'm frankly not sure how to do 33, other than to just stumble through it. So perhaps we do this. So do you understand what question 33 is asking? Okay, beautiful. Okay, so that gives me a sense of where to start. So let's try this. HCl, HBr, HI, HCl, that's not an L, oh, poop, it all went away. Do not laugh at my pain. All right, starting again. HCl, HBr, HI, HClO3, HClO4, HNO3, H2SO4, which, guys, collectively, you would better begin to start to have a sense. These 7 dudes are all on the board because they are all strong acids. Guys, remember we said that after Labor Day, we were going to start talking about holding you accountable for that quiz? Well, Labor Day was yesterday. So, guys, what I'm not going to do is have you worry about this before the test. I will allow you to bring resources into this first test, including that sheet that gives you the strong acids. But, guys, understand, after that first test, it's now time to spin this up. With that said, starting, Sophia, maybe the way to approach this question is all of these are strong acids, but they are also all molecules where we have a hydrogen bonded to another thing that is also a negative ion when it forms salts. So, for example, chloride, bromide, iodide, ClO3, ClO4, nitrate, and sulfate. So all of those things are also on our polyatomic ion sheet. Okay? All right. So what the question is asking you then is this. And obviously, because they're asking the question, we know the answer is yes. But the question is, how do these ions then behave in solution in salts. And so, guys, let's look at chlorine, bromine, and iodine. And I know you're working on your solubility rules, but maybe you're not there. But guys, chlorine, bromine, and iodine are all halogens. And what are the things that we think about relative to solubility with halogens? They're soluble in water unless silver, lead, and mercury, right? So, guys, this is not a coincidence. These three ions are also ions that form soluble salts. Well, guys, let's keep going. ClO3, ClO4, I don't even know solubility rules about those. Do any of you? I don't either. But I'll tell you what, I know about nitrate. What do we know about nitrate? They all dissolve in water. Now, guys, what about sulfates? Should we go look? Yeah, grab your books. Let's go back to table 4.1 and let's take a look because there are sulfate rules. Page 121. What do we know about sulfates? They do dissolve in water, with a few exceptions, and those exceptions are some heavy group 2 guys and then lead 2, which seems lead and mercury, which both seem to be exceptions to all the rules. But guys, sulfate substances also tend to be water soluble. So, Sophia, that's the point that they're trying to get you to, is that the same ions that form the strong acids are also the ions that tend to form soluble salts. Is that okay? Okay. Guys, however, don't do this. These are not salts. You guys understand that, right? In these compounds, the hydrogens are not ionically bonded to the ion. They're actually covalently bonded. Remember, hydrogen is a freakishly strong metal that stands its ground even against some pretty electronegative characters. And so, guys, these are covalent bonds. They're not ionic bonds. But when they break, they do form ions even though they're covalent bonds. So, number 33. Sophia, was that sufficient? Okay, so what else, y'all? What else do you want to talk about? Y'all good? Okay. So, guys, let's get this in the books. All you need is note-taking materials today. No calculators, none of that business. So, guys, I'm going to have to, I think I can do this. Yeah, because I'm recording. So I have to be careful about how I do score recording. All right, Braden, are you good? Donnie, you good? Yep. Sophia? Yeah. Annika, you good? Yep. Ishmael? Yeah. Josh? Yeah. Diana? Yep. Chandler? Yes. Isaac? Yep. Ellie, you good? Landon, how about you? Yep. Nathan? Yep. Emma, you good? Emma, you good? Sorry, yeah. Okay. Sorry to interrupt. Max? Yeah. Leslie? Did you say no? Yes, no? Yes. Yes, yes. Gage, how about you? Ronnie, you good? Kaylee? Spencer, you good? And Daniel? Meredith, you? All right. So, guys, did any of you print the notes? Oh, wait, did I post them? You don't even know, so I'm not going to incriminate myself. Guys, super, super duper short today. Short homework, and you'll notice this 1, 2, 3, 4 slides. Oh, yeah. So, guys, at the risk of saying something that's out of line, but tipping our hats to Dr. Martin Luther King Jr., guys, I have a dream as well. My dream is this. My dream is that when those 3 words, well, here, do I even have a title slide? There we go. When these 2 words show up on the screen again, and this is going to be in late mid to late March. Guys, when these words come up again on the screen, we will be starting the last unit of the year. Chapter 20, it will lead us into spring break. Coming back after spring break, we will spend every day getting you ready for the AP test. But guys, understand what we are about to cover very briefly today will be an entire unit when we get to the end of the year. My dream is that this happens here and not online. If we can make it to this, we made it through the year, and I'm excited about the prospect. But guys, understand, this is a big idea. In the same way that acids and bases are big ideas, this is also a big idea that we are going to cover very, very superficially. There's a couple little ideas that you need to understand. There are some equations that you need to know how to balance. But guys, understand, this is a big idea that we're going to cover superficially. So this is called oxidation reduction. You guys ready? So let's define some terms. So guys, when we talk about oxidation reduction, we've got to define the terms. So scratch this down with me. So guys, when we talk about oxidation, we are simply talking about a losing of electrons. But, and I know you can figure this out, but we may as well write it down. So guys, when a substance loses electrons, what happens to their charge? Does it become more positive or more negative? More positive. So the thing that's losing electrons, its charge becomes more positive. Guys, that process is called oxidation. Now, not surprisingly, there is a competing process. That process is called reduction. And I'm guessing I don't need to tell you that reduction would be the gaining of electrons, and the thing that's gaining electrons, its charge becomes more negative. But guys, this provides a good opportunity to have sort of an interesting conversation that I think will help you make sense of this. Where do the names come from? Why do we call the losing of electrons oxidation? Why do we call the gaining of electrons reduction? And I don't ask it rhetorically. Guys, think through it. Let's take oxidation first. Why would they call the losing of electrons oxidation? Well, what's the root word of oxidation? Oxygen, right? Okay, so let's have the talk then. Guys, what do we know about oxygen? Well, oxygen is in the upper right-hand corner of the periodic table. So what does that tell you about its electronegativity? It's very strong. Now let's talk about the Lewis dot structure for oxygen. Can you picture it mentally? How many pairs of electrons are around that oxygen, around the oxygen atom? So in its valence shell, oxygen's got how many pairs of electrons? 2. So it's got 6 valence electrons. 4 of them are paired up. What about the other 2? They're unpaired, right? So guys, the Lewis dot structure for oxygen looks like this. Can you now figure out why we call the loss of electrons oxidation? What do we know about oxygen? It really wants electrons, and it's got space to put them, right? Guys, oxygen is the perfect electron stealer. I mean, if you think about something like fluorine, fluorine could be a good electron stealer, but once it gets one, it's done. Nitrogen could be a good electron stealer, but it's not electronegative enough to be a good electron stealer. It's actually a better electron donor. That's why nitrogen-containing compounds are bases. They share their electrons. So guys, oxygen is sort of the perfect candidate. It's very strong, it's got room to put electrons, and it's also very plentiful. So let's then think about what oxygen does, for example, to metals. Guys, if you take a chunk of metal, if you take my stapler and it's made of steel, and you sit my stapler outside for a year or so, what's that dude going to look like? It's going to be horribly rusted. Well, guys, what's going on when something rusts? What does it take to make something rust? Oxygen. Guys, what's happening is oxygen actually starts to steal electrons from those iron atoms. When it does, it creates iron oxide compounds that we call rust. So guys, rusting is actually an oxidation reduction process where oxygen is stealing electrons from metals. When it does, it forms these oxide salts that we just call rust. But guys, that's all rusting is. Yeah. Well, and actually, so it needs water to happen quickly. And Nathan, it's a great question. So in some places it does. Like in very, very humid places, deep south, stuff rusts just sitting in your room. But here it's so dry that we need water. We need, and so water, it's interesting how water gets involved in the process, and we'll talk about it in chapter 20. But really it's the oxygen that's causing the rusting. Go ahead, Spencer.
How about like the corrosion is with the other things that burn up, and part of it doesn't corrode, so that can burn.
It can, right. It's also an oxidation so but it does. Yeah, so guys, let's talk about quickly what Spencer's saying. And it's neat that you know this, that when iron rusts, when iron hooks up with oxygen, it does this very violently and it can burst into flames. But so does iron. Guys, you know those little heat packs that you can actually stick inside your gloves? Do you know what's in there? It's just very, very small iron filings and a catalyst that causes the iron to react with oxygen. So when you take one of those heat packs and rip it open, all you're doing is exposing it to the oxygen in the air. But in the presence of a catalyst, it speeds up the rusting process and it releases enough heat that it doesn't burst into flames, but it warms your hands. Because that's all that's in one of those heat packs is actually just iron that rusts in the presence of a catalyst. So if we speed up rusting, it actually does. It is exothermic. It releases heat. So, absolutely. So, guys, oxidation then, are we settled on the idea? Oxidation, taking in of electrons. They originally called it oxidation because the first evidence of it was rusting, and they knew that oxygen was stealing electrons from metals, so they called the process oxidation. See how that all fits together? So why then reduction? Because where does the name reduction come from? Exactly. Yeah. So guys, that's exactly where it comes from. We've established that the thing that's being reduced gains electrons and its charge goes down. So guys, if you're looking for a way to sort of remember this, you may want to write this down. The charge of the particle that's being reduced is reduced. Its charge goes down. Now guys, if you like that, that's great. But you need to be able to keep oxidation and reduction separate. You need to be able to identify that oxidation is a losing of electrons and reduction is a gaining of electrons. If you like this little idea of the charge of the thing that's being reduced is reduced, that's fine. Up at the University of Utah, they teach this little mnemonic, oil rig. Oxidation is loss, reduction is gain. If you like oil rig, that works too. Yeah. Oh, heavens, no. No. Yeah, no, and thank you. Well, it was the first one. Thank you for calling that to point. So, guys, please do not think that oxygen is the only thing that can oxidize things. No, there are oxidants that are like crazy, scary, terrifying, like rip electrons, like the rocket motors that we use to send satellites, to send nuclear weapons into space, is basically a big old tank full of kerosene, and then this oxidizing agent that will like rip holes in cities, like it's crazy. And so no, there are other oxidants that are just terrifying. So no, it doesn't have to be oxygen. But guys, they called it oxidation because it was the first example they saw in rusting. So again, guys, you got to be able to tell the difference between oxidation and reduction. Oil rig gets you there as well. You good on the idea? Let's bring them together, then let's look at some examples of what you need to be able to do with this. So guys, fundamentally then, it brings us to the idea of what are called redox reactions. So guys, in a redox reaction, we now honor the fact that these things have to happen in pairs. So fundamentally, guys, if we're going to have oxidation, which is the loss of electrons, those electrons have got to go somewhere. And the place that they go then is to the thing that's being reduced. So you can't have oxidation without reduction, and vice versa. You can't have reduction without oxidation. Something has to be losing, something has to be gaining, and bringing those together, we call these redox reactions. And we call this redox chemistry. So guys, a redox reaction then is a reaction in which electrons are being exchanged between substances. But guys, this then is where this starts to get interesting, and this is the first skill that you've got to have. So guys, here then is the question. If a redox reaction is an exchange of electrons, then guys, how on earth do we know that electrons are being exchanged? What do we look for to see that electrons are being exchanged? And the answer is, we look for charge changes. When we analyze redox reactions, guys, what we're looking for are actually charge changes. So the first thing that you've got to learn how to do, guys, is assign oxidation numbers, charges. You need to learn to assign oxidation numbers to substances. So guys, what I'm going to do, and forgive me for doing this way, but what I'm going to do is I'm going to give you the 6 rules for assigning oxidation numbers. I'm going to have you scratch these in your notes. I just realized I need to go set up Miss Call's lab. I did lab first period and didn't move everything over. Guys, scratch these in your notes. I'll be back in 3 minutes. We'll talk about what they mean. One more thing to do and we're done for the day. No, you didn't. What I meant to say, guys, let's talk about these one at a time. Here we go. All right. So guys, rule number 1 when you're assigning oxidation numbers. All of the elements are understood to have oxidation numbers of 0. So elements don't have charges. And again, guys, I don't expect you to understand what this means. We're building framework that we're going to apply in just a minute. So rule number 1, if it's an element, its charge or oxidation number is 0. Rule number 2, for a monatomic ion, its oxidation number is equal to the charge of the ion. And guys, we'll explain more about what that means in a minute. I want to let you get these on paper, and then we'll talk about them. Then guys, rule number 3, nonmetals typically have negative oxidation numbers. Remember, they're electronegative and they like taking in electrons. Then guys, number 4, hydrogen can go either way. If you put hydrogen with a nonmetal, it'll go +1. If you put hydrogen with a metal, it'll go -1. Which may make sense. Nonmetals tend to be negative, so hydrogen goes positive. Metals tend to be positive, so hydrogen goes negative. And guys, again, I know these may be a little obscure and confusing, but as we talk about them, it'll become more clear. And guys, rule number 5, the sum of the oxidation numbers for all the atoms in a compound is 0, and the sum of the oxidation numbers for all the atoms in a polyatomic is the charge of the ion. And gang, again, I don't expect you to understand any of this, but it'll give us a common language that we can talk about. As we get started. So gang, once you get these written down, what I'd like to do is I would like to give you a little more insight into rules 1 and 2, and then we'll start messing around with these, and then it'll start to make more sense as a whole. You guys good? Y'all caught up? Can we start talking about this? Okay. So guys, rule number 1 says that all elements are understood to have a charge of 0. So functionally what that means is if you've got any element, I mean, it doesn't matter. So take nitrogen's a tough example at first. Take, for example, iron. If you have a chunk of iron sitting there on your table, if you have a chunk of lead sitting there on your table, guys, these elements have not gained or lost electrons. Therefore, their oxidation numbers are understood to be 0. Remember, oxidation numbers tell you how many electrons they gain or lose. And if they're elements, they have neither gained nor lost. Therefore, it's 0. You get the idea? Okay. This is where this becomes a little different. Nitrogen. Guys, remember nitrogen you never find by itself. Nitrogen is diatomic. But guys, this is the elemental form of nitrogen. Nitrogen does not exist on its own, so this is also understood to have an oxidation number of 0 because it's in its elemental form. It just happens to be diatomic. And that also applies to iodine, bromine, chlorine, fluorine, oxygen, and hydrogen. Remember, guys, these are the diatomics, and their oxidation numbers are understood to be 0 when they're diatomic. Is that okay? Okay. Then, guys, let's talk about this second rule. This is a little weird. So let's take, for example, so we've been sort of talking about this all along. So, guys, take sodium, and sodium has a charge of 1. So the question is, which one of these is correct? Is it sodium 1 plus, or is it sodium plus 1? Here's the trick. Guys, we have been saying that they're interchangeable. In fact, they're not. Guys, this is the way to represent sodium when it loses an electron. This is the way to represent sodium when it shares an electron. So guys, the idea is if the number comes first, that is the charge of an ion. If the sign comes first, that is an indication of how many electrons it's sharing, not that it's losing. But then, guys, we get to point number 2, and what it basically says is the oxidation number, which is this one, is the same as the charge, this one. So, guys, rule number 2 is basically saying we've been writing 1 plus or plus 1, and we've been using those interchangeably. Rule number 2 says they are in fact interchangeable. Oxidation numbers, which talk about how many they potentially could lose, are the same as their charges, which is how many they did lose. So it seems obscure. If I hadn't included rule number 2, you never would have caught the difference. In college, they make a big deal out of this. But for now, guys, just understand they are in fact interchangeable. You guys okay? All right. So now, guys, let's start taking the rest of these rules and start applying them. So, guys, scratch this down, skip down 2 or 3 lines, and write it big. And that's the thing that is interesting about AP chemistry, Spencer. You're exactly right. That in general chemistry, we protect you from all of the exceptions. And in AP, we talk about all the exceptions. And then the rules become, many times the rules just go away. There's no longer always and nevers. Absolutely. So guys, did y'all get this down? Here's what you need to do. You need to be, this is a skill you've got to have. Guys, you have to be able to assign oxidation numbers to all of the elements that are in this compound. So guys, first of all, let's do this. Is this compound a salt or a molecule? It's a salt. Can you name it? K is potassium. What about MnO4? Do any of you know? It's one you need to know. Have any of you got to it? Begins with a P, permanganate. So guys, this is the salt, potassium permanganate. So guys, let me help you think through how to think about this relative to the rules that we just learned. So you may want to write this down with me. So guys, the first thing that we know is this. This entire salt has an overall charge of 0. We know that because we have a rule that says compounds have a charge of 0. So guys, when we're done with this, the entire thing has to have a charge of 0. But now, guys, what we're going to do is we're going to start mentally teasing this apart. So if we were to, and this is a strong electrolyte, if we were to put this in water, where would it break? Between the K and the MnO4, or the KMN and then the O4? Yeah. So it breaks here. So from that break, we can now start assigning charges to pieces. So guys, what is the charge of potassium? It's group 1. What's its charge? +1. But guys, you'll notice that I wrote it backwards. Its charge, and you don't need to write this down, its charge is +1. So is its oxidation number. That's what that second rule says. Technically, we know that because when we put this into water, potassium loses an electron to MnO4, and it becomes potassium +1, 1 plus that we would write like that. The oxidation number tells us how many electrons it could lose, and in this case it's 1. So the charge and the oxidation number are the same. So guys, if this is +1, what has a charge of -1? The Mn or the O4? Neither. What has a charge of -1? The whole thing. Guys, this entire thing right here has a charge of -1. So I'm going to get this 0 out of the way because that's kind of distracting. So guys, that entire thing has a charge of -1. That's what it, well, and we'll keep building from there then. So guys, given that information, we can now figure out the charge of the oxygen and the manganese. So I know that you don't have this advantage and you won't, but let's talk. So guys, if you look at manganese, even from a distance, can you see that it's got like 11 different charges? But if you look at oxygen, what is the charge of oxygen always? -2. So guys, oxygen is always -2. Oh, oxygen is always -2. So if that's true, what does the charge of manganese have to be? Let's do this. So guys, oxygen is -2, but there's 4 of them. That gives us a total negative charge of -8, which means manganese needs to be +7. Why? Because the entire ion is -1. Guys, let that sink in. That's what it's talking about when it says the charge of polyatomics. The oxidation numbers for polyatomics add up to their charge. If MnO4 is -1, and if oxygen is -2, giving us a total charge of -8, then manganese has to be +7 in order to give this entire polyatomic an overall charge of -1. Go ahead, Spencer.
But you like put it into a metal or like the Mn, so like how do you get the metal in this? Like
I'm not following your question.
like the second element to be right, how do you make that a metal?
Well, but remember, this metal is tied up in a polyatomic. And because that's true, what we've got is a molecule, a polyatomic ion, then ionically bonded to another metal. It does not. This metal forms a molecule with oxygens that then forms a salt with potassium. I agree. So guys, what do you think? Are you okay with this idea of assigning oxidation numbers? Does that sit okay? Okay. So guys, with that then as a background, this is what we need to be able to do with this. And this then is how we are going to wrap up the day. And you're going to have more than enough time to get your homework done. So guys, when we now look, and think about how we've done this. When we talked about precipitation reactions, remember we talked about writing net ionic equations. When we did acid-base chemistry, we talked about the reactions that are gas-forming reactions. We talked about neutralization reactions. And we talked about the reactions when the base is a solid. Well, guys, in the same way, when we talk about oxidation-reduction reactions, we're going to talk about the types of reactions they normally carry out. Well, guys, these reactions are generally single displacement reactions. And what you're going to see is that these single displacement reactions are typically a metal in its elemental form either being ionized by an acid or a salt. So guys, we're going to look at one of each, and we're going to turn you loose on some homework. So Nathan, this actually kind of gets a little bit to your question earlier as well about why do metals rust more readily when they're outdoors. I mean, we understand we're talking about aqueous chemistry, right? So this happens more efficiently in water, but also when we're outside, there are more salts readily available to also kind of encourage the process. So, guys, we're going to look at these one at a time. Let's do this one first. Let's talk about the oxidation of a metal by an acid. So, guys, let's go and let's actually look at a reaction that you may actually remember. Do you remember that lab that we did? We did this one, right? The lab where you took the zinc and you dropped it in the hydrochloric acid and you flipped the test tube over up above it and you collected the hydrogen gas and you stuffed in the wood splint and went boop and y'all giggled and you did it. Did we do that lab? We didn't get to do that lab. Oh, you guys got robbed. As if you needed another reason to be bitter about COVID. You guys missed the giggle lab. Oh, man. We really didn't do that lab? Well, no. Well, we're going to next period. But, no, it wasn't an acid-base lab. It was the reaction types lab. All right. Well, we can write out the chemistry anyway. You do remember giggling. That's good. All right. So, guys, whether we did this or not, this is a classic oxidation reduction reaction. Take a piece of zinc like this, huck it into a test tube full of hydrochloric acid, and guys, we end up with a single displacement reaction taking place. So guys, let's tear this thing apart. When this thing goes through a single displacement reaction, what are our products? Well, guys, does the zinc hook up with the hydrogen or the chloride? Chloride. Zinc is a metal, it's positive. Chloride is negative. And guys, zinc is actually +2, so it forms ZnCl2. And then guys, what happens to the hydrogen? It bonds to itself, and it goes away as a diatomic. So guys, this is the single displacement reaction when hydrochloric acid attacks zinc. But it is also an oxidation reduction reaction. Your challenge is going to be to figure out what is being oxidized and what is being reduced. So guys, to do that, what do we need to know? Oxidation numbers. Do this with me. What is the oxidation number of zinc? 0. It is in its elemental form. Does that now make more sense? Okay. Now guys, let's look at HCl. Hydrogen is with a non-metal. So if hydrogen is with a non-metal, will it be positive or negative? Positive. So hydrogen is +1, chlorine is -1. Now guys, let's take a look at zinc and chloride. Chloride is still -1. But why did we need 2 chlorides to hook up with the zinc? Because zinc is now +2. And then guys, what is the oxidation number of hydrogen? 0, because that is its elemental form. By the way, guys, we should balance this. You guys good? Okay. So now, the last thing we need to do, guys, is we need to track electrons. Whose charges are changing? Did zinc's charge change? It did. So do this with me. So zinc's charge changed. What about hydrogen's charge? Also changed. What about chloride's charge? Did not change. So now, guys, let's pull this together and let's talk about who is gaining electrons and who is losing electrons. So, guys, zinc went from 0 to +2. So did zinc gain or lose electrons? It lost electrons, and specifically, it lost 2 electrons. Now, guys, what about hydrogen? Hydrogen went from +1 to 0. So how many electrons did hydrogen gain? 1. But there's 2 of them, right? So 2 hydrogens each gained 1 electron for a total gain of 2 electrons. Now, guys, what if those numbers are not the same? Then you balance the equation improperly. You're going to find out in chapter 20 there is actually a law of conservation of electrons. But guys, for now, all you need to know is that those should match up. But now, guys, please do this with me in your notes. I'm setting you up for failure because this is an important point. I'd like you please to write a couple sentences in your notes. Write out what was oxidized and what was reduced. Blank was oxidized. Fill in the space. Blank was reduced. Fill in the space. If you're a typical group, nobody in this room will get both of these right. Fill in the blanks. Blank is being oxidized. Blank is being reduced. We're not talking about it yet. So guys, let's try this. Blank is being oxidized. Oxidized means what? Gaining or losing electrons? Losing electrons. So what fills in the blank? What is being oxidized? Zinc. Zinc is being oxidized. Now guys, let's try the other one. Blank is being reduced. Reduced means gaining electrons. What is gaining electrons? Not hydrogen. Nope. What is gaining electrons? Guys, if hydrogen were gaining electrons, then that would be gaining electrons because that is hydrogen. What is gaining electrons? Well, this is gaining electrons, but that is not hydrogen. Hydrogen is a gas. What is this? Hydrogen ion. Those are not the same. Guys, hydrogen is a diatomic gas. Hydrogen ion, which is actually the thing that's gaining electrons, are simply protons. They couldn't be any more different. And guys, it's critical you understand that. It is not hydrogen that's gaining electrons. It's hydrogen ion that's gaining electrons. And those are not just semantics. Guys, ions are so completely different than their elements. In the same way that chlorine is a brown, deadly gas and chloride tastes delicious on our fries. They couldn't be any more different. So make sure you're clear on that. You guys good? Yeah? Okay. Now here's what I'd like you to do. Somewhere on your paper, draw the beaker. And guys, draw in that beaker what this reaction looks like. What do you got? Do not include the water other than to draw a water level. And guys, understand, you're going to be drawing pictures all over the test next week. You're going to be drawing pictures all over the AP test. That's why we spend so much time drawing pictures. So guys, and Daniel, that's a good question. As you're drawing this, draw what would be in the beaker when the reaction is like half over. While it's reacting. You okay? Can we fiddle with it? So guys, let me offer to you a strategy, and I'll just tell you right now, when you do this on the test, what it'll look like on the test, because this is what it looks like on the AP test, you will actually see 3 beakers. Beaker number 1 is draw one of the reactants. Beaker number 2 is draw the other reactant. Beaker number 3 is draw all the products together. But here we're going to do them separately. So guys, what about this? While this reaction is taking place, what does the zinc look like in the beaker? Guys, it looks like this. It's a chunk of metal. So down here at the bottom, you should have a chunk of zinc. But then the zinc is in a beaker of HCl. So will there be any HCl's in the beaker? No. Why not? It's a strong acid. It completely breaks apart. So we will have hydrogen ions and we will have chloride ions in solution. Then guys, what about over here on the right? And please don't miss this. This is the tricky bit. Is there any zinc chloride in this beaker? There's not, because we know that all halogen-containing salts are water-soluble unless they're bonded to silver, lead, and mercury, and that is not this. So guys, this will actually be broken into ions, so we will have zinc ions, and then we will have more chloride ions. And then guys, what does the hydrogen look like? Bubbles. So maybe we could write like an H2 up here as a bubble as that stuff goes away. Now guys, do this. Take your pen or pencil and cross out the spectator. What is the spectator in this reaction? What is it? Chloride. It starts as an aqueous, it ends up aqueous, and so it is chloride that is our spectator. So then, guys, what is the net ionic equation? It's zinc plus 2 protons yields zinc ion and hydrogen gas. That would be the net ionic equation. What do you think, y'all? Yeah, Ronnie. No, thank goodness no. Because if this chlorine came together and formed, if the chloride came together and formed chlorine, we would end up killing, I mean, that's mustard gas, right? But Ronnie, let's talk about how we know that's not the case. So this is a salt, no different from sodium chloride salt. And we know that when, well, different metal, but they're both salts. So when we put table salt in water, we're comfortable with the idea that that breaks into sodium ion and chloride ion. Well, the same thing is true here. When this is in water, it exists as zinc ion and chloride ion. So these chlorines are never bonded together. They would actually, and I don't think I can really fake this. It's gone. I don't think I can fake this very well. But if we could look at the crystal structure, so it would be like, you know, this isn't great, but you'll get the idea. That it would actually look more like this. That it would be a zinc with 2 chlorines and then another. Well, here, let's just see if we can look it up. Rather than fake it, let's actually explore. So it would go like that, like this, clean this off. So zinc, chloride, crystal structure. So this kind of gets us there, sort of. So the reds are the zinc and the greens are the chlorides. Oh, that's cool. That's actually an electromicrograph of it. That's pretty neat. Oh, here we go. So maybe this. So the chlorines are the green, the zincs. So you've got a zinc and 2 chlorides, and it repeats. So, but that's the idea. The thing to notice is the chlorides are not bonded together. They are separated into individual ions. Is that okay? Yeah. So that's the idea. Okay. So guys, let me get rid of this, jump back over here, pull this mess back up. You guys feeling okay about that? Let's do one more. So this could freak out. Let's see. Nope. Okay, so we got that one. Guys, now let's talk about the oxidation of a metal by a salt. So let's do iron dumped into a beaker of copper 2 sulfate. All right, guys, it's in your court. Predict the products. Figure out what is being oxidized and what is being reduced. And then write the net ionic equation. You got about 3 minutes. You know what, guys? Let's do this. Sorry, I hope this doesn't cause you great concern. But rather than iron, oh, my screen's frozen. Rather than iron, let's make it zinc. I doubt that messed you up too bad. So let's go zinc plus copper 2 sulfate. It has the same charge as iron, so it won't mess you up too bad. But you'll see why I switched in a minute. We can talk to Susie. Susie. Susie makes everything better. All right. You guys okay? Are you caught up? Can we talk about it? Let's talk about it. So we'll keep this here for now. I'll jump over here. You need another second? Okay, let's do it. So, guys, first thing we need to understand is that this will be a single displacement reaction. So does the zinc hook up with the copper or the sulfate? Sulfate. So we're going to end up with zinc and sulfate. Zinc is +2, sulfate's -2, so there you go. And then, guys, finally, copper gets singly displaced. So then, gang, we need to assign oxidation numbers to these guys. So what's the oxidation number for zinc? 0, because it's in its elemental form. Copper is +2 because the entire sulfate is -2. And maybe that's a bad place to write that. Let's do it like this, and we'll say the entire thing is -2. Now, do we need to assign oxidation numbers to the sulfur and the oxygen? And the answer is sometimes, but not this time. And then the question becomes, how do we know? Well, guys, let me show you. Keep going. So now we come over to zinc. Zinc is now +2, and sulfate is now -2. And then let's finish this up. What's the oxidation for copper? 0. So guys, how do we know that we didn't need to break up the sulfur and the oxygen and assign oxidation numbers? And the answer is because this didn't change. Its charge didn't change. Its structure didn't change. Because it didn't change, it's not doing chemistry, and therefore the oxidation numbers of the parts also didn't change. So if that's true, what did change? Well, let's look. So did the oxidation number for zinc change? Yeah. I like to connect them. What about copper? You bet copper changed as well. So guys, what happened to zinc? Did it gain or lose electrons? So zinc lost 2. Yep, and that means that zinc was oxidized. Then guys, copper, and I'm going to say this wrong, but copper gained 2. Yes, and that's the point. And I know that you're sort of tentative now, but guys, copper ion gained 2 electrons, and it became copper metal. So copper ion was reduced, zinc metal was oxidized. And then guys, what about sulfate? Did it change? So what is it? Spectator. This is our spectator. So the net ionic equation is zinc metal plus copper 2 plus ion yields zinc 2 plus ion and copper metal. But guys, this time, rather than have you draw the beaker, what I'd like to do is show you what this looks like. Well, we'll let Susie show you what this looks like. Guys, this is the reaction.
When a zinc rod is immersed in an aqueous...
Sorry. All right, Susie, try this again.
When a zinc rod is immersed in an aqueous solution of copper sulfate, a similar oxidation-reduction reaction occurs.
So guys, this is actually what's happening at the atomic level. This is our zinc, copper's in solution.
In this reaction, zinc is again oxidized. Now, however, copper 2 plus ion is reduced to copper metal.
So guys, the zinc atoms are releasing electrons to copper ion, just like we said. Can I do this? Oh, I can't do it. But if you look at what you wrote in your notes, you'll notice you've got zinc 0 becoming zinc 2 plus. So the zinc metal is losing electrons to copper ion. Copper ion becomes an elemental metal, and then the zinc ion goes into solution. Oh, will it let me? Oh, there we go. Oh, let's do it again.
When a zinc rod is immersed in an aqueous solution of copper sulfate, a similar oxidation-reduction reaction occurs. In this reaction, zinc is again oxidized. Now, however, copper 2 plus ion is reduced to copper metal. In the two examples...
And this is where we'll actually go with this later in writing half reactions. But that's the idea. So guys, you good? How about a little homework? 45 through 53 odd. We will look at this on Thursday. We will wrap up the unit on Thursday. Test will be Monday because we actually used the period. We have a few minutes left. We will break at 10:10. We will come back and turn in a bunch of lab stuff, and then we'll go over to lab. And that'll do us. So if you want to start a little, you have a few minutes. But we'll look at these on Thursday.